Imagine a region of space so extreme that not even light can escape. A place where mass is so densely packed, space and time themselves are warped beyond ordinary comprehension. This is a black hole, one of nature's most dramatic phenomena. In this video, we'll explore what exactly a black hole is, how it forms, what its structure looks like, how we detect it, and why scientists care so much about them. First, what do we mean by a black hole? The word is a little misleading. It's not just an empty void. Rather, it's an astronomical object whose gravity is so intense that nothing, not even light, can escape once crossing a certain boundary. In more formal terms, a black hole is a region of spacetime in which the escape velocity, the speed needed to break free, exceeds the speed of light. The key boundary that defines it is known as the event horizon. It's not a physical surface you could touch, but rather the point of no return. Because nothing can escape beyond that boundary, the interior is hidden from external observers. Hence, black. How do black holes form? The most common route is via the collapse of a massive star at the end of its life. When a star much more massive than our Sun runs out of nuclear fuel, its internal pressure can no longer support it. So gravity takes over and the star implodes, potentially producing a black hole. But black holes come in different sizes. Stellar mass black holes are formed from individual collapsing stars, typically tens of times the mass of the Sun. Supermassive black holes, millions to billions of times the Sun's mass, are found in the centers of many galaxies. There may also be intermediate mass black holes, hundreds to thousands of solar masses, and primordial black holes, hypothetical objects from the early universe. The exact origin of the largest black holes is still an active area of research. What does a black hole look like? And what's inside? While you can't observe the interior directly, the theory gives us several key features. In classical general relativity, the mass collapses to a point of infinite density, called the singularity, where space-time curvature becomes infinite. The event horizon is the boundary around the singularity beyond which nothing can escape. From the outside, this is the visible boundary of the black hole. Matter falling toward the black hole typically spins, heats up, and emits radiation, often X-rays, before crossing the horizon. This forms the accretion disk, making black holes indirectly observable. For rotating black holes, space-time itself is dragged around the hole, creating unique regions like the ergosphere. According to quantum effects near the event horizon, black holes might emit very faint radiation, known as Hawking radiation, and slowly lose mass. One common misconception: a black hole doesn't suck in everything like a vacuum. From the outside, its gravitational pull behaves like any other object of the same mass. It only becomes extreme very close to the horizon. Even though black holes themselves emit no light, scientists have multiple ways to infer their existence. We detect them indirectly through stellar orbits, where stars orbit something invisible. For instance, stars near the center of the Milky Way orbit a very compact, massive object, identified as Sagittarius A star. Accretion signatures, like matter falling into a black hole, heating up and emitting X-rays, provide bright signals that betray the presence of a black hole. Gravitational waves, ripples in spacetime generated when two black holes merge, can be detected on Earth, confirming their existence and properties. Direct imaging by the Event Horizon Telescope collaboration captured the shadow of a black hole in galaxy M87 in 2019, providing visual confirmation. Together, these methods make the case for black holes extremely strong. Why are black holes so important in astrophysics and cosmology? They test the limits of physics, extreme gravity, space-time curvature, singularities, and event horizons all push our theories to the edge. They play a key role in galaxy formation and evolution. Many galaxies host supermassive black holes, whose growth influences the galaxy's central region. They connect general relativity with quantum mechanics, Phenomena like Hawking radiation and the information paradox raise deep questions about how gravity and quantum theory unify. They serve as cosmic laboratories. By studying black holes, we learn about extreme states of matter, high-energy astrophysics, and possibly even the early universe. In short, black holes aren't just oddities. They're central actors in the story of the universe. So what is a black hole? It's a region of space-time where gravity wins so completely that even light cannot escape. It may originate from the collapse of massive stars or from the hearts of galaxies, and it features a boundary called an event horizon, beyond which nothing returns. While you cannot see the black hole directly, the effects around it, swirling accretion disks, energetic jets, warpings of space-time, or gravitational waves, give away its presence. Black holes challenge our understanding of space, time, matter, and energy. They're extremes of nature, pushing physics to its edge. But with every observation, from stellar mass companions to supermassive giants, from gravitational wave signals to the image of a black hole's shadow, we come closer to unraveling their mysteries. Thank you for joining this journey into the darkest light of the universe. Quick roundup of myths versus facts. Myth: black holes roam the universe and swallow everything in sight. Fact: a black hole's gravitational pull is like any other object of the same mass. You have to be very close to the horizon to get sucked in. Myth: you can see a black hole directly. Fact: you cannot see the black hole itself, as no light escapes. You see effects around it, or its shadow. Myth: black holes last forever. Fact: according to theory, Hawking radiation suggests they may eventually evaporate, though for most known black holes this timescale is enormous. These clarifications help keep the awe in check while still appreciating how extraordinary they are. Now that we know what black holes are, let's look at the vital roles they play in shaping the cosmos. For decades, astronomers suspected that these invisible giants might sit quietly at the centers of galaxies. But modern observations revealed something spectacular. Black holes are not passive. They sculpt the galaxies around them. The energy released by gas spiraling into a supermassive black hole can drive enormous jets of plasma that stretch for thousands of light years. These jets can heat, compress, or even blow away gas clouds, the very material from which new stars form. Paradoxically, black holes can both create and quench starbirth. They act as galactic thermostats, regulating how galaxies grow over billions of years. In a sense, every time you look up at the Milky Way, you're seeing a system delicately balanced by the invisible hand of the black hole at its core. In 2015, humanity heard the universe for the first time. The Laser Interferometer Gravitational Wave Observatory, or LIGO, detected tiny ripples in spacetime caused by two black holes colliding over 1 billion light-years away. The signal lasted only a fraction of a second, a rising tone scientists nicknamed a chirp, but it confirmed Einstein's last untested prediction. Since that historic detection, dozens more have been recorded. Each tells a story. Two black holes orbiting, merging and becoming one. From those waves, we can measure their masses, spins, and even estimate how often such collisions happen across the cosmos. It's like learning to hear an entirely new kind of astronomy. Gravitational wave astronomy, where the universe becomes not just something we see, but something we can listen to. One of the strangest effects of a black hole is how it distorts time itself. Einstein's relativity tells us that the stronger gravity becomes, the slower time flows. Near a black hole, this effect becomes extreme. If an astronaut hovered safely outside the event horizon and looked outward, the universe beyond would seem to speed up. Stars evolving, galaxies aging, billions of years passing in moments. To distant observers, that same astronaut would appear frozen in time, never quite crossing the horizon. This is called gravitational time dilation. It's not science fiction. It's been confirmed on smaller scales using satellites and atomic clocks. But near a black hole, it becomes almost infinite. Time itself bends, stretching to eternity. So what if you fell into one? Approaching the event horizon, you'd feel gravity changing dramatically between your feet and your head. This difference in force stretches your body like spaghetti, hence the term spaghettification. If the black hole were small, those tidal forces would tear you apart long before you reached the horizon. But if it were a supermassive black hole, like the one in our galaxy, the gradient would be gentler. You might cross the horizon without noticing. Inside, the laws of physics as we know them stop working. All paths lead inward. Space becomes time. Time becomes space. The singularity awaits, a region of infinite density where our equations fail. No one knows what truly happens there. Does matter collapse into a point? Does quantum physics prevent the singularity, or could it open into another realm of space-time? A wormhole, a bridge to elsewhere. These questions mark the frontier of modern theoretical physics. In 1974, physicist Stephen Hawking changed everything. Using quantum theory, he discovered that black holes are not entirely black. At the edge of the event horizon, pairs of tiny virtual particles constantly flicker in and out of existence. But near the horizon, one particle can fall in, while the other escapes. To the universe outside, that escaping particle looks like radiation, what we now call Hawking radiation. Over unimaginable spans of time, this slow leak causes the black hole to lose mass. Eventually, it could evaporate completely, ending its existence in a final flash of energy. For a supermassive black hole, this process takes longer than the age of the universe. But it shows that even the darkest objects may someday fade into light. Hawking's discovery led to one of the greatest puzzles in science, the black hole information paradox. Quantum mechanics insists that information about matter can never be truly destroyed. Yet if black holes evaporate, what happens to the information about everything that fell inside? Does it vanish, breaking quantum law? Or is it somehow encoded on the event horizon itself? Some scientists propose that the horizon acts like a hologram, storing every detail in two-dimensional form. Others argue that new physics, perhaps a theory of quantum gravity, will reveal the answer. Whatever the outcome, this paradox sits at the intersection of the two great pillars of science: general relativity and quantum mechanics. Solving it could unify them into a single theory of everything. Far across the universe, astronomers see objects so bright they outshine entire galaxies. Quasars. Their light began its journey billions of years ago, from when the cosmos was still young. At their cores lie supermassive black holes consuming vast amounts of gas. As matter falls inward, it heats to unbelievable temperatures, releasing radiation that travels across space. Quasars are the cosmic lighthouses of the early universe, showing us how the first galaxies and black holes grew together. By studying them, scientists can peer back in time, to within a few 100 million years of the Big Bang, and trace how these titanic engines shaped everything we see today. Black holes may seem distant and abstract, yet they speak to something deeply human. They remind us of the limits of our understanding and the power of curiosity. Every discovery about them, from Einstein's equations to the first image of a black hole's shadow, represents centuries of imagination, mathematics, and perseverance. They are nature's laboratories, pushing our theories to breaking point and forcing us to rebuild them stronger. Perhaps one day, a future civilization will travel close enough to study them directly, using technology we can only dream of. Until then, our telescopes and our minds remain our time machines, letting us explore these cosmic mysteries from afar. So, what is a black hole? It's not simply a hole in space. It's a triumph of gravity, a place where matter and energy collapse into pure geometry. From the tiniest stellar remnants to the giants anchoring galaxies, black holes connect the smallest quantum scales with the largest cosmic structures. They challenge everything we know about physics and everything we think we know about ourselves. They remind us that even in total darkness, there can be revelation. That sometimes, by studying what we cannot see, we learn the most profound truths of all. The universe still holds countless secrets, and at its deepest center, black holes are whispering them, waiting for us to listen. If you enjoyed this video, your engagement is invaluable. Please comment below, share your thoughts, and connect with our community. Please also like, share, and subscribe to our channel. Your support encourages us to create more engaging content for you.